All, welcome back to AK Logics. In the previous class, we have discussed about the full header code in the behavioral model. How to write the full header code in the behavioral model. Okay, yeah. In this today's class, we are going to discuss about the data flow model. How to write the behavioral code for the data flow code for the full header. Okay, yeah, we are going to explore the levels of abstractions using an example that is full header, right? So if you haven't watched those videos, I recommend you guys to watch those videos and then only return to this video. Then only you will have a continuity in the learning process. Okay, if there is no continuity in learning, then you might get confused, and also it's very difficult to learn everything in detail. So that I request you guys to watch those videos and then only return to this video. Okay, so without any delay, let's start the video. Today we are going to discuss about the data flow model. Okay, what is meant by data flow model? Okay, yeah. So next, let me take the pen. Yeah, levels of abstraction in that type 2 is the data flow model. Okay, in the previously we have discussed about the type 1, that is behavioral model. So now we are going to discuss about the data flow model. Okay, we write VHDL program based on the Boolean expression of the output. Okay, we write basically this particular data flow model using the Boolean expression of the output. Okay, in the previously we have written the code using the truth table, but in this we are going to write the code with respect to the Boolean expression of the output in terms of input, right? So next example, let's take an example. For example, if I'm going to take an AND gate, we have input ports two, those are A and B. These are the input ports, and the output ports are one only, that is Y, right? This is output port, this is input port, right? These things we specify in the entity itself. Okay, what are the inputs, what are the outputs, we are going to specify this thing in the entity, right? Next, we are going to take the truth table for the AND gate. Then for the all the inputs of R1, then we are going to get the output as 1. For remaining cases, we are going to get the output as 0. Okay, if you can see the any one input is 0 to the AND gate, then we are going to get the output as 0, and also any one, if the both the inputs are the 1 to the AND gate, then we are going to get the output as 1. Yeah, so this is basically the behavioral model. If you are going to write the behavioral model using this particular truth table, you are going to write the code. Okay, you are going to write the code for the this particular AND gate. Okay, that thing we have seen in the previous case for the full adder, right? If you are going to write if you want to write the code for the AND gate, just you simply use the if else condition, if else if condition, which we have discussed in the previous class. Then we can able to write the code in the behavioral model. Next, what is meant by data flow model? So in the data flow model, what we are going to do is we need to use the keyword, that is AND, right? This is the keyword which performs the AND operation. In the previous class also we have used this particular keyword in the behavioral model when we are going to use the if else. In that if else parenthesis, we have specified A equal to quotation 0 and B is equal to quotation 0 and Cin is equal to quotation 0, then sum equal to 0, that is sum less than or equal to 0, and then sum cout less than or equal to 0. Yeah, so I think something happened, right? Yeah, basically how we are going to specify in the data flow means, if you are going to take the output as Y and we know that the inputs are A and B, then you need to specify like this: Y less than or equal to A and B. The thing A and okay and B, and then we are going to use the semicolon. Okay, yeah. So here and is a keyword, right? Here and is a keyword. This thing is not clearly visible, so that I have written the statement which is in the box, white box. So and is a keyword. Okay, it's not the user defined. Okay, A and B are the user defined, which are the inputs and outputs. Okay, and this particular less than or equal to is a assignment operator. Okay, this particular thing less than or equal to is a assignment operator. Okay, it's simply like an equal to. Okay, for any VHDL program, the entity is same for any program, whereas the architecture depends upon the user interest, that is based on the levels of abstraction is for the architecture, right? For any VHDL program, the entity will be same, right? In the architecture part, while defining the logic relationship between the inputs and outputs, we have three levels of abstraction. Those are behavioral, data flow model, and then the structural model. These things only will be varied for any VHDL program. But the entity which we are going to specify before the architecture is same for any levels of abstraction, right? Yeah, that point you need to remember. And also we are going to write the architecture for that entity only. Okay, for that entity only we are going to write the architecture. What I'm going to say is, previously I have taken the entity FA full header. For that entity only, what you have going to do is, you have in the architecture you have given that architecture behavioral of FA, where FA is the entity name, right? So that's the point. We are going to write this architecture for the entity only, right? Yeah, so that entity will be same for any level. If you are going to use any level of abstraction, then the entity will be same. Next example, let us take the same example. In the previous case, we have three input ports for the full adder and also two output ports for the full adder. Now let us see. This is the truth table, and from this truth table, we are going to get the Boolean expressions for the outputs. We are going to have the two outputs, those are sum and cout, and three inputs, those are a comma b comma c in. This is c in, not c. There is a mistake. We just correct it. In the previous class also, I think so, there is a mistake. Yeah. So next, by applying the K-map, okay, we are going to get the Boolean expressions for the full adder output from the truth table using the K-map. Okay, sum equal to A XOR B XOR C in, and also C out is equal to AB plus BC in plus C in B. These are called as the Boolean expressions of the outputs in terms of inputs. Okay, how we are going to get this is using the K-maps. Okay, let me pause this video. For the sum, if you are going to take the K-map, then what happens is, so we are going to take the minterms. Okay, this will be 0, right? Minterm 0 and 1 and 2 and 3 and so on up to 7, right? Why? Because we are going to have the three input variables, then we are going to have the total 8 combinations. Those are from 0 to 7. Okay, this thing we are going to learn in the digital electronics. So that we are going to write the first expression for the sum. So that the expression for the sum is 1 2 and then 4 7. So that we are going to put these values as 1 1 2, and in KMF we are going to use the gray code. Okay, which is having the unit distance between the two adjacent cells. Okay, so that 1 2 and 4 and then 7. Okay, 4 and then 7. Okay, we are going to map, right? There is no possible pairs and quad or any oct, right? So that we are going to take as it is those things. We are going to take as it is. So if you are going to solve this expression, okay, we are going to get an expression. Then if you are going to solve the expression, then you are going to get the sum result as sum is equal to AX or B X or C in. Okay, so I am not going to solve those expression. Why? Because if you doesn't know even solving that example, then I recommend you first just go through the digital electronics and then only visit this particular VHDL or any Verilog series. Okay, not only in my channel or any other channel. You first go and visit digital electronics thoroughly. Okay, so that's the, then only you feel very comfortable learning the VHDL and then Verilog. So that I am not solving the equation, so it will take time. So that I'm not going to by, because my handwriting is very dirty, and then the video length is getting running, so that you will lost your patience. Okay, so that I'm not going to write those things. So you will get an expression. Okay, let me erase this. So we have written the sum expression, right? There is no possible pairs or quads or any octs, right? So now what we are going to do, right? Similarly for the carry, let's see. For the carry, see out, that is in the position of 3, and then 5 and 6 and 7. Okay, 3, 5, 6 and 7. Okay, there are possible there is a possibility of getting pairs. Okay, this is one pair. Okay, this is one pair. From this pair we are going to get, what we are going to get is B seen, right? Because this is the 1 and 1. It means in the SOP we are going to mention 1 as the non-complement form, that is normal form, whereas 0 as the complement form. From this we are going to say that this is, for this particular pair we are going to have the common values that are B and C in, whereas A is getting changed, right, from 1 to 0, right? There is no common of the A, so that common thing is B and C in, so that from this pair we are going to get the B C in. And from another pair, let us see, from, whereas from this particular pair, sorry, you can't able to visible, so it can't yeah, from this pair. Okay, from this pair, okay, what we are going to get horizontally, if you are going to say, there is common A is common for the both the cells. Okay, 5 and 7. So one thing is A is common, and if you are going to see above like this and also above like this, then you can see that Cin is common, right? Cin is common, there is one and also there is one, whereas B is getting changed from 0 to 1, so we need to take it as a Cin, sorry, this is wrong. You need to take it as A Cin. Okay, A Cin. Okay, it's a printing, it's a mistake from my side. So A Cin, and then if you're on the last pair, let us see, and then last pair, let us see, if you are going to take the last pair, this is the pair, last pair, then you can see that in the horizontal direction the A is common for the both the cells of 7 and 6. A is common, and then if you are going to say vertically above, from the both the cells, then you can see that here there is 1 1 and here there is 1 0. It means B is common, B is 1 in the both the cells, right? B is 1, right? B is 1 in the both the cells, whereas Cin is getting changed from 1 to 0, right? So from this particular pair we are going to get the AB, right? From this particular pair we are going to get the AB. Then we are going to do the OR operation between them. Then we are going to do the OR operation between them because it is an SOP, right? So like this we got this cout expression, and also I told you about the sum expression. Now taking those from which we have got these expressions, mean from the truth table and from the K-maps. So we got the expressions of the outputs. So using these expressions we are going to write the code in the Dataflow model. Okay, yeah. So code, again, in the previous case what we have taken in the behavioral model, same entity we have taken. Why? Because the entity will be always same, only the architecture will be varies. Why? Because in the entity we are going to just mention only the what are the inputs and outputs. We are not mentioning any relations between the inputs and outputs, but this level of abstraction is basically the different ways, tells the different ways of representing the relationship between the inputs and outputs, right? So that where we are going to mention the relationship between the inputs and outputs is in the architecture itself, so that the architecture only will changes, the entity will always remain same. So that only, say, the previous class I have told, right, entity is a keyword and FA is the entity name and easy is a keyword, I forgot to mention it. Okay, yeah. And then port, in the port we have declared the three input ports in and STD logic and some cout, which are the which are in the output mode, and then STD logic, and then end FA is the entity name. Okay, this is all about the entity. And coming to architecture, we are going to take the architecture and we are going to specify a name for the architecture. That is, I am going to use this data flow. Why? Because I am going to write the code in the data flow model, so it will be meaningful whenever any person who doesn't know about any coding, then he can able to know that this is the style of Dataflow model by seeing this particular name of, and then I am using the entity name, right, which is I have given in the above, that is FA, and then I'm using the is. Okay, after is, what I told, if you have any signals, intermediate signals, then you need to specify after the architecture data flow of FKEs. Okay, after this point you need to specify if you are going to have any intermediate signal, but in this case we don't have any intermediate signals. Why? Because we have direct expressions of the Boolean expressions of the outputs in terms of inputs. So that I'm going to use the begin. In the begin, what we are going to write concurrent statements. What concurrent statements are the statements which are going to execute in the parallel manner. So that we are going to use the sum, which is one output, sum less than or equal to a XOR b XOR c, in where XOR is a keyword, okay, which is used to perform the XOR operation between the a and b, and then the resultant value to the c in, and then I have used a semicolon, and for the another port, that is c out, less than or equal to a and b. Okay, we need to specify it in the parentheses. Okay, you must remember this point, a and b, or b and c in, or, and then a and c in. Okay, semicolon. Okay, and I have entered the architecture which I have begin, and data flow, which is the name of the architecture. So like this way we are going to write the architecture for the full adder in the data flow model. Okay, this is way this is the way of writing the code of full adder in VHDL using the data flow model. Okay, here we are going to use the Boolean expressions. In the previous class, while we are going to discuss about the, while we have discussed about the behavioral model, we have used the truth table. Okay, using that particular truth table only, we have got the expressions of the Boolean expressions of the input, Boolean expressions of the output in terms of input. Using those expressions, we have written the code. That particular code is called as the data flow model of the full adder. Okay, this is all about the code. So if you like this video, please like. Yeah, so in the next video we're going to discuss about the structural model, how to write the code in structural model. Okay, we have seen already two styles. Those are the behavioral model and then the data flow model. In the next video we are going to see about the structural model.